Okay, so welcome everybody. All right, so where did we leave off? So more on characteristic method, more on method of characteristics. You might notice your first homework, uh, every single equation on your first homework was linear. So we're going to do a bunch more linear examples because practically speaking, those are kind of the most instructive because those are the ones that you can do basically from scratch on your own with very little reference to pretty much anything other than the stuff you already did in Math 246 or ODE, any of your previous experience for ODE. That's pretty much all you need. Um, Unfortunately, moving into more more complicated equations, so semilinear, quasi-linear equations, requires a little bit more finesse because the ODE, the characteristic ODEs that result are nastier, and they're likely a type of ODE that you never learned any kind of like systematic approach to, because for most of them there's not really a systematic approach to them, and so you have to kind of rely on other things to solve them. So those are ones that you can't necessarily just be turned fully loose on. Um, not entirely, anyway, at this point. But anyway, nevertheless, we are going to do all of those. We're going to try to do pretty much everything, even including the fully nonlinear case. Although I will truncate that coverage a little bit when we get to it. But anyway, let's see more linear examples first. So uh, let's do the example as follows. So let's see here. So let's say we have PDE that is minus y u sub x plus x u sub y is equal to u. And the auxiliary condition is, again, a specification on the y-axis of some data function g. Okay, so let's see kind of how this goes here. So first of all, let's recall the characteristic equations. So I don't have the page from last time, so let's go ahead and actually, I'll just bring this up on camera here. So let's see, let's make sure that that is decently readable. All right, so okay, here's my method of characteristics for linear. Here is the most general form for a linear first order PDE. All right, so this is the notation we use. So if the PDE you're given is not in this form, you need to put it in this form so that everything makes sense, of course. So we are good because our x and y partials are on the left-hand side along with their coefficient functions, of course. On the right-hand side, we have u or any inhomogeneous term. So here we just have a term on u where the coefficient function on u is just constant function 1. And this c sub 2 function, of course, is 0. Okay, so we exactly have this linear first order PDE. And in that case, the characteristic equations look like this. Right? So here's my characteristic equations. Now, of course, they are paired together in this way. But we saw in our first example that we were actually able to do these first two equations together, right, separately from this. Then we were able to do this equation for z, and then based on this we were able to figure everything out. Remember, this notation here, z is actually the value of u along the characteristic, right? So the z of s is actually the value of the solution along that characteristic curve, and that characteristic curve is parametrically x of s, y of s, right? Okay. All right, so that's just reminding you how this goes. Okay, so then let's get back to this. So what does our characteristic equation look like here? Well, what this means then is that remember, the characteristic itself is parameterized by parameter s, and there is its parameterization. Okay, so then the ODE system governing trajectories for this thing is what, according to the characteristic equation? Well, it would be x dot, remember this is the derivative with respect to this parameter s. It's x dot is equal to minus y, and y dot is equal to the coefficient function on the y partial here, which is x. Okay. And then we also have a z dot. What is this equal to? Well, z dot is equal to, let's bring back the characteristic equations real quick. So z dot is the coefficient function c1, which in our case is 1 for this example, times z, plus the coefficient functions, or sorry, this inhomogeneous part c sub 2, which in this example is 0. And so this is actually just z dot is equal to z. Now you might notice that this third equation can be solved without reference to the first two, right? So we could definitely do that and find an answer to this in terms of an initial, an initial point x naught and s. But we need to solve these anyway to finish this, so we might as well start here. Also, there are going to be plenty of examples, we'll do one next, where you can't do, this third equation can't be done without first doing these. Okay, and so as usual, we start with these first two and solve those. Okay, so then how do we solve these first two? Well, got to remember some ODE stuff. So I'm not typically going to do this for the most part. When I see something like this, I will say ODE tells me here's the solution. Okay, so let's just quickly do this so that you can very quickly remember how this sort of thing was done in Math 246, and then that will be on you for the rest of these. But so recall from Math 246 what we can do here for an equation like this. So remember, this is an example of a system, right? So let's so here, this is a complete aside here. I don't want to spoil the rest of the problem with what I'm writing here in terms of notation. So let's say that we have a vector, right? And this is the notation I'm going to use. So I have this vector x bar containing, if I write it as a column vector, so here is my column vector xy. This system of first order ODEs, since first order linear ODEs, this is nice as possible here that I can hope for. This is written in the form of x prime, where I've taken the derivative with respect to this parameter, is equal to ax, right? For A, some 2 by 2 matrix, right? A is some 2 by 2 matrix. So let's do this. If I write this out here, this would be like x. I'm just going to write it as x dot since I wrote it here. Be x dot of s, y dot of s is equal to A, which I'll write, it's just a generic 2 by 2, A, B, C, D, times the vector x of s, y of s. But this is, I can just write this out, right? This is x dot in this case would be 0 x minus 1 y, and this is y dot of s is 1 x plus 0 y. Okay. All right, that this is that system. And so it's a linear system where A is 2 by 2 matrix, 0, minus 1, 1, 0. Now, there were a number of methods you used to do this, and to find, say, a fundamental solution set or a natural fundamental solution set to a system like this. The easiest, kind of most straightforward one is eigenmethods, right? So recall eigenmethods, kind of the most direct thing to do here. So basically what you did is you found eigenvalues of A, and then based on that, you wrote out your solution, right? There was like a canned recipe that allowed you to write out the solution set here. And so this has eigenvalues, what, like plus or minus I, right? If we actually wrote it the characteristic polynomial, so eigenvalues for this one are plus minus I, which leads to, I'll draw an arrow over here, which leads me to say that the general solution to this system is the following. X of s is some constant. If I'm calling this C1, C2 here, then we'll say this is C2 cosine S minus C1 sine S, and y of s is C1 cosine S plus C2 sine S. Okay. All right. Now, here, of course, is where we do some kind of standard trickery for method of characteristic stuff. Now, if this was just an ODE problem, then what would we do here? We would want to specify these constants by imposing some initial condition or whatever, right? That's how this is done. But here, you know, this is just our intermediate step to solving this problem. So these C1 and C2, these are not really constants, right? These are constants. We used scare quotes around these things, right? So these are constants. But we need to choose these in a way that makes this make sense for our initial data here. Right? For the initial data and for then the characteristics that those things determine, or that are determined by this data curve and those initial or auxiliary values for u, right, that are listed here. So, so what do I do? What does that mean? Well, let's draw quickly our domain. So our domain, whatever this is on as much of the plane as I can here, except I have this. Let me get another color. So my data curve is the y-axis, which is pretty typical here. Okay, so here's my data curve. At some point here, right, x naught 0, I have a characteristic, right, like emanating from this point. As I think about it, or at least I have a characteristic that intersects this data curve at this point. Okay, and so in order to impose conditions on these constants that make my characteristic, remember the characteristic is parameterized by this, so these are telling me the trajectories here. I need to initialize these in such a way that this characteristic is intersecting this y-axis, or sorry, this x-axis here, at s equals 0, right? So at s equals 0, I want x of 0, y of 0 to be equal to this thing. I want this point to match up with this, right? I want those two things to be equal. Okay. So then what I want is for, here, let me buy myself some space here. So what I want is x of 0 to be x naught, and y of 0 to be 0. And so what does that? I need to choose C1. I need to choose C1 to be 0, and I need to choose C2 to be x naught. So that will do it here. And so what do I get, right? I want x naught to be, or I want x of 0 to be x naught, y of 0 to be 0, and so this implies that I want x of s to be x naught cosine s, and y of s to be x naught sine s. All right. And so that is what my characteristic looks like, right? Those are the trajectories. Now you might notice, you know, you don't have to do this at this point, but it might help just with your understanding of what's going on here. What is this, right? If you were to plot, right, x naught cosine s, x naught sine s, like what is that? Well, if here is x naught, then what is the trajectory, what is the characteristic curve that for this problem that intersects the x-axis at x naught? Well, here is the parameterized characteristic curve. It's just this. It's x naught cosine s in the first slot, x naught sine s in the second slot. We know this is just a circle of radius x naught, right? This is circle of radius x naught centered at the origin. And so the characteristic that intersects the x-axis at x naught is that circle. If x naught had been chosen to be this point, it would be this circle, and so on, right? Oh, that was pretty terrible, but you can use your imagination here that that's supposed to be a circle. So so any of these points, right? The corresponding characteristic that that passes through them intersecting the x-axis at that point is exactly the circle centered at the origin of that radius, right? That point specifying the radius here. Okay, so that's exactly what the characteristics look like. All right, which will help us a little bit later when we're thinking about how to do this. Okay, let's bring back our characteristic equation. So we have solved these first two. As I mentioned earlier, we actually could have solved this third one on its own without reference to this at all. We wouldn't have been able to completely find the solution here. We would still need to solve this. But these two are kind of like unpaired, right? They're like, I could do this and I can do this totally separately, and then I combine them to get the actual solution. That's not always going to be the case, though. So sometimes you're going to need to do this first in order to even be able to approach this problem. So that's why this is how we usually start this, because this is an atypical thing that you can separate this process like that. So anyway, oh, I took it way too fast. So here's our characteristic equation. So z dot is equal to z. Again, that has solution from Math 246, which is actually not so bad, right? This is just, so I'm looking for function in parameter s that is equal to itself, right? Its first derivative is equal to itself. So that's not too bad. This is z of s is some other constant. So to not confuse it with these two constants, I'm going to pick another constant, c sub 3 here. That's what I'll call it. But c sub 3 e to the s, right? This is my z of s. Okay, I'm just going to copy that down on my next. So we found by solving the third equation that z of s is some constant c sub 3 e to the s. Well, again, we have to impose an initial condition here. So one, so what are we thinking? So first of all, z of 0 is what? So z of 0 is u of x of 0, y of 0. Okay. But we chose the values of those constants in these equations specifically so that x of 0 is x naught and y of 0 is 0. So this is really u of x naught 0 is equal to z of 0. But u of x naught 0, of course, by our auxiliary condition, is just g of x naught. Right? And so we have the condition z of 0 is equal to g of x naught, which means that actually the form that z of s takes is g of x naught e to the s. Okay. Now we're almost done here, right? So what is the idea? So the idea for given arbitrary point xy. So here, right? Find characteristic corresponding to it. So we want to, rather than in this picture, I drew this characteristic first and then I put this on it. But imagine that that wasn't there and I just picked some point. So like here is another point I could have picked. I need to find the characteristic, right, that corresponds to it. So I would need to find the x naught, whatever it is, right? Here, there it is, that corresponds to it. Of course, like I said, this is a circle of that radius centered at the origin. But what this really means, of course, is i.e. find x naught and s corresponding to this point xy. But then in the context of this problem, i.e. for generic xy, find x naught and s such that x needs to be equal to x naught cosine s and y needs to be equal to x naught sine s. But for a given point xy, find x naught and s such that x is x naught cosine s and y is x naught sine s. You know exactly what this is, right? In fact, if I had labeled x naught as r and s as theta, then you'd recognize that this is just polar coordinates, right? Of course you recognize this polar coordinates anyway. So this is polar coordinates. Right, this is polar coordinates. So if x and y are defined in this way, right? If I'm looking for an x and y such that x is x naught cosine s, y is x naught sine s, then what do we know? We know by polar coordinates that x naught squared is x squared plus y squared, and s, our theta here, can be found by, well, this is arctan of y over s, right? Sine over cosine is tan. This is arctan of y over x. So this is just going backwards from polar coordinates, well, backwards or forwards, depending on what direction you're talking about. Okay. And so, x naught squared is x squared plus y squared, so x naught is square root of x squared plus y squared. So all I need to do is plug these expressions for x naught and s into my expression for z. Right? So therefore, plugging into z of s, which we said was g of x naught e to the s, we obtain the solution u at a generic point xy is equal to g of x naught square root of x squared plus y squared, e to the s. S is arctan of y over s, or x, sorry. And this solves our original PDE. Let me bring it back. It looks like this. Now, you can check that this actually solves this PDE here. Notice that the form this takes, this is something you're highly unlikely to have been able to guess, right? Just looking at the PDE. So, you know, this is, even in the linear case, this yields solutions that would otherwise be pretty hard to come about, right? Okay, now, as I mentioned a couple times previously, in our characteristic equations here, we didn't actually need to do the system first. We actually knew that z of s was going to have this form, right? So we knew z of s was going to have this form. And just by imposing initial conditions in a way, we'd be able to figure out, you know, this constant involves this g. Like, so without solving this, we'd be able to kind of find a general form of this. We wouldn't be able to get the actual solution without doing this, but we'd be able to find kind of a general form of this. But that's not always going to be the case. So in many cases, you are going to have to do this first in order to be able to solve this last equation. Here we could separate them out. Not always going to be the case. So here's an example where we can't separate them out like that. So I'll do that next. One thing before I move on, though, is you can note that there is actually an issue with this solution at the origin, right? So note the solution is undefined at the origin. There's a couple of things to think about here. So one, what are problems? If we're looking at the characteristics, then we notice a problem, right? So here's our picture of characteristics. The problem, of course, being that, yeah, as we get closer and closer and closer to the origin here, these are still circles, but as we get to the origin, now this curve is degenerated into a single point, right? The characteristic curve then is just this single point. That doesn't really make sense to us. That's one thing. But if we go all the way back to looking at the actual equation that we started with, at the origin, because of these coefficient functions here, x and y, then at the origin, this term is 0 and this term is 0. And so this PDE is degenerated into like not a PDE, right? Because both of the terms that actually involve the partial derivatives are no longer present. You may remember the exact sort of thing happening back in Math 246 when you had a coefficient function on like your leading term in a differential equation, where that coefficient function would be 0, and it would cause the equation to degenerate to be a lower order equation. Or in the example of first order equation, if you had a coefficient function wherever it was 0, technically you weren't dealing with a differential equation anymore because that derivative term was vanishing. But for first orders, the way you dealt with this is you put the first order into like linear normal form, and so you divided through your equation by that first order, that coefficient function. Well, of course, when you divide through by a function, then whenever that function is 0, you're going to have issues. And so that was typically how it came up in 246. Was in order to solve the problem, everything you did, every recipe you did, assumed that you had already put the differential equation into linear normal form, which involved dividing through by the coefficient function of the leading derivative term, right, the first derivative term. So now, in your expression, you didn't have anything multiplying your first derivative term, but you divided through by it. So wherever that was 0, right, corresponded to a point where that first derivative term would have vanished if you hadn't divided through by it, right, wherever that coefficient function is 0. So now you're dividing by 0 wherever that leading coefficient function was 0. So anyway, that's typically how it arose in 246. But for us, we see, like, you can see it in a number of ways. You can see the characteristics degenerating at that point, or you can just look at the equation and say, oh, well, like the equation is degenerating in the sense that like both of the partial derivative terms are vanishing, so it's like not even a PDE at that point. Okay. All right. So let's do another example here. So let's find solution of the following. So let's say u sub x plus u sub y plus u is equal to e to the x plus 2y. And let's say that our data curve function, again, this is the x-axis, is just 0, right? Okay. All right. So here, again, recall the characteristic equations. What are my characteristic ODEs, first of all? So the coefficient functions on u sub x and u sub y are both 1. So my characteristic ODEs for those are x dot of s is 1 and y dot of s is also 1. Okay. So then solving this isn't too bad. Right, we're happy here. This is like s plus a constant I'll call c1, and y of s this is s plus a constant I'll call c2. We're looking for characteristics, of course. This is telling me the trajectory here. I want to pick this in such a way, right? Choose c1, c2 in such a way that at s equals 0, my initial point, right, x of 0, y of 0 lies on the x-axis, right? So again, this is the choice that I make. All right, so if I do that, then I want c1 to be x naught and c2 to be 0, right? And so x of s is s plus x naught, and y of s is s. Okay. All right. Now, let's return to these characteristic equations for z. So recall, Z dot is C1, this coefficient function, and this is the coefficient function on U when this U term is on the right-hand side of the equation, plus the coefficient function C sub 2, which is this inhomogeneous term on the right-hand side. So this is a little different. What is this then? Well, now the ODE for Z of S is, by the characteristic equations, this is Z dot of S is what? So this U is on the left-hand side, but I need to put this here. Just real quick. Let's put this in, you can call it normal form, I guess, if you want to. Let's put this in the form that the characteristic equations are stated in, right? So this would be minus U plus E to the X plus 2Y. Okay. All right. And so Z dot of S is what? This is minus 1 is the coefficient function on U here in this form. So this would be minus Z of S. Right? Again, remind yourself, here is my characteristic equations, C1Z plus C2, where C1 and C2 are these coefficient functions. Okay. So this is minus Z of S plus the coefficient function C sub 2, which is e to the x plus 2y. Now, here's the thing that I have to remember, right? I can't, like, x and y can't really show up here because this is an ODE where the parameter in question is s. It doesn't really make sense for x and y to show up as some kind of like independent variables, right? That doesn't make any sense. So I use the fact that the characteristic has this form, right? X is s plus x naught, and y is s. And so that e to the x plus 2y becomes e to the s plus x naught plus 2 times s. So that's s plus 2s plus x naught. So that's 3s plus x naught. So this is plus e to the 3s plus x naught. So that is why all I've done here is taken x plus 2y, and I've used these instead. So for x, I've put in s plus x naught, and for y, I've put in s. And so this is what I get. Okay. All right. So by ODE, what is this? This is first order linear inhomogeneous. I can do this by, right, this is like my most general linear equation. I can do this with integrating factor, right? So I can do this immediately via the integrating factor recipe, right, that you, I'm sure, had memorized by heart in some form in Math 246. So what is my solution here? This is Z of S is 1/4 e to the 3 s plus x naught plus constant C1 e to the minus s. So if you like, you can remember this is via integrating factor. Okay. So how does this help me? Here, I want to leave this right here. So again, we're always looking to determine any of these constants that show up here using the previous things we've done with the characteristic. And so what do we say? Well, z of 0 is what? Z of 0, of course, is u of x of 0, y of 0. X of 0, y of 0, let's pull that back, right, have to be equal to x naught 0. I don't know, did I point to the right place? Yes. And so this is u of x naught 0, but of course our data for this problem, right, so here's my PDE plus auxiliary condition, 0 on this data curve. And so this is actually 0. So if this thing is going to be 0, imposing that condition here, right, 0 is z of 0, which means that this is 1/4 e to the x naught plus c1, right? And so c1 is like minus 1/4 e to the x naught, right? Okay. So using this for our generic z of s, so z of s is 1/4 e to the 3s plus x naught minus 1/4 e to the x naught times e to the minus s. So if you like, you can write this in a little bit more convenient way as, I'm just going to write it like this. This is 1/4 times e to the 3s plus x naught minus e to the x naught minus s. So there's my z of s. There is my value of the solution along the characteristic. Okay. Okay. So now what? Well, again, for a generic xy, I want to find, so for a generic xy, I wish to find an x naught and s corresponding to them, i.e., what did we do to do this last time? We used the characteristic curve, right? So I'm looking for what? I'm looking for an x that is s plus x naught, or sorry, s plus x naught, and a y that is s. So I'm looking for an x that is s plus x naught and a y that is s. Well, that's not too hard to find, right? So I'm looking for an s. There it is. It's just y. The first one tells me that x naught is x minus s. So this is x minus s, which is x minus y. All right, so x naught is x minus y. Y is s. And so my solution, that's my solution to the PDE is, all I need to do is plug in these for x naught and s, into z, right? So this is u at a generic point in my domain is 1/4 times e to the 3s, right, plus x naught. So this would be like x plus 2y minus e to the x naught minus s. So this would be x minus y minus y. So x minus 2y. This would be e to the x minus 2y. You can check that it satisfies the auxiliary condition, right? If y is equal to 0, this is definitely identically 0. And also solves the PDE. Okay. And so there's another good example. This is also a good example because, as I mentioned, notice how in order to even write out the differential equation involving z, I had this inhomogeneous term, which meant that I had an s and an x not showing up here, which I needed to, like, how did I get this showing up? I got this from this previous equation for x and y, allowing me to nail down what the characteristics look like. Okay, so that's how all of that worked. So the nice thing about well, maybe this is a little bit subjective, but the nice thing about the method of characteristics, especially for the linear case, is that it's fun. It's fun to find like what the actual like general form of these things looks like for equations like this, because even for relatively simple equations, it can be kind of like very complicated and interesting, and it's fun to get to the end process and actually get some kind of closed form explicit solution. It's really fun, and it's not something you get to do that much for PDE, beyond first order stuff. So that's what makes it even more fun. Okay, although, as I said, I guess you can't fully appreciate how fun it is in that way until you've seen the higher order stuff and kind of what happens. Okay, so let's do a couple more examples before I talk about kind of doing more general equations, which our next step into the more general equations is going to be pretty quick, because the semilinear case is taken over by the quasi-linear case, and we'll talk about both of those, because in fact we actually have a quasi-linear example we will do before actually writing out the characteristic equations in the quasi-linear case, just because it's very instructive to kind of talk about what it is that's going on here. Okay, and so let's talk about temporal equations or time-based equations, right? So just as I mentioned previously in Math 246, the convention was if you had a first-order differential equation, this wasn't just true for first-order differential equations, it's true even for higher-order linear first-order equations. Whatever coefficient function multiplied the time derivative term, you divided through by it, okay? And so similarly for a first-order PDE that involves, like variables in some number of variables x1, x2, and time, the typical convention is that we would write a first-order PDE like this. Right, and I mean, of course, we can move stuff on the other side, but the idea is that whatever my coefficient function is on the u sub t term, I divide through by it. I can always put it in this form. The textbook doesn't really have a name for this. I'm just going to call it the usual form. So the usual form for a temporal equation. Right, notice that we didn't do this when we were dealing with, say, like two spatial variables x and y. We didn't do this. We left the coefficient functions there. There's a reason for thinking about it like this. The main reason for doing this is the following. So if we do this, all right, if we move that coefficient function onto the other functions, then what happens? Then the characteristics, or I should say the corresponding characteristic equation for our t variable now, so then say our data is given on the t-axis. Okay, or maybe I should say not the t-axis, we'll say the t equals 0 axis. We'll be careful here. Okay. Then the characteristic equation corresponding to this, because the coefficient function is 1, is just t dot is 1, right? Okay. And of course, if we have, say, initial condition t of 0 is 0, then what this yields is that t of s is just s, i.e. t is equal to s for my characteristic. So the parameter t and the parameter s are the same. Well, if s is the parameter for the characteristics, right, that we've been using. And so thought of in this way, our characteristics, right, now don't have the variable s, they have the variable t. So then our characteristics then take the form. So our characteristics now are going to take the form like x of t and then t, right? So actually, rather than having to do these things parametrically, I can just think of like t as the x of t, a scalar equation that tells me what these characteristics look like. Okay. And the thing that's nice about this is because in the specific like applications or the situations in which these equations are modeling, it actually makes sense to do this, and we're going to get some nice interpretations of what the values of our solutions mean and things like that. So for instance, let's do an example here. So this is transport equation with variable speed. Okay, so let's consider the following. So consider the PDE, use of t minus x, use of x is equal to 0. And we'll say that our initial data here is this function 1 over 1 plus x squared. Right? Okay. And so what to think about. So we know that this is an example of a transport equation here, where our normal transport equation is like use of t plus c use of x equals 0, where c was a constant. Here now it's variable, so that c was our speed before, so now this speed is variable here. And we have some initial data. We could think about this as like a signal. Of course, if you plotted this real quick, what would this look like? This is like that. Something like that. The textbook calls this like a blip. You can think about this as a blip. Okay, we'll be using functions like this to think about blips here. Notice, you might say, well, like things I've seen described as blips, they might do something like this instead. It's like 0, and then does this. And that's true that something like this may be more thought of as a blip, whereas this, we would say this doesn't have compact support, which means it doesn't vanish off a compact set, right? That's how this thing is, right? This thing is never zero, whereas this thing is zero everywhere except on some compact set centered at zero. Fine, but this can still be thought of as a blip in this way. There's nothing wrong with this, and we're gonna talk about both sorts of examples of these things. So don't, this is not a super technical term here. Okay. So anyway, if we think about this being like a blip signal here, I have transport equation with variable speed, and we'll worry about this for t greater than or equal to 0. So then we have some like initial disturbance, our blip here, and so we want to know like how this propagates, right? Like how this signal propagates according to this transport equation, how the signal is transported. So what do I do to look at my characteristics, right? So looking at my characteristics, from the characteristic equations, I have dx dt is, so dx dt is minus x, dz dt, again, you might say, why are you writing this out? Normally, don't you have x dot and z dot? Yeah, I'm writing it out, though, to make sure that there's no confusion. Remember, because we're doing this bit by normalizing or dividing through by this coefficient term, I have this simple characteristic equation for t, so that I can think of t as being the parameter of my characteristic. So it's t that I'm taking these derivatives with respect to. Of course, it's really s I'm taking the derivatives with respect to. It doesn't matter because t and s are, those are going to be the same thing here. So dz dt is 0, right? And so I can solve, of course, both of these things. So first of all, this one tells me that x is x naught e to the minus t. And this one tells me that z is constant with respect to t, but because it is equal to this signal, right, at the initial point x naught corresponding to this thing, this is, so z of t is, or I'll just write it as z here. I mean, it's the same thing, but I'm suppressing notation here. So z is 1 over 1 plus x naught squared. Okay. Okay. So I want to do the same thing that I've been doing, right? Which is, okay, now I have like t and s are the same thing, right? So that t is my parameter s, x is the other thing. So given it's the other independent variable. So given xt, I want to find, now you might say x naught and s, but I've already found s. It's just equal to t. So I want to find x naught such that blah, 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 right? X is equal to x naught e to the minus t. But if that's the case, that means that x naught is just x e to the t. Right? And so our solution is u of xt is 1 over, well, as we saw here, here's z, 1 over 1 plus x naught squared, but x naught is x e to the t. So this is 1 over 1 plus x squared e to the 2t. So that's what this looks like. In order to see kind of more clearly what this is, I can do a little bit of algebraic manipulation here. I can multiply this by e to the minus 2t over e to the minus 2t, so that this becomes e to the minus 2t over e to the minus 2t plus x squared. However you want to look at this. And now let's plot profiles of this. for, we'll say t equals, say t equals 0, 0.5, 1, 2, and 3. What would this look like? Well, it would just be me generating these graphs for various fixed values of t and seeing what happens in my x versus t plot, right? So let's, rather than draw out those plots, let me give you a nice picture here. So here are those profiles. So here's the initial blip, right, and how that affects this thing being transported. Here is at t equals 0.5. Here's t equals 1, t equals 2, t equals 3, t equals 4. So think about that compared to the profiles that we saw for the transport equation previously for constant speed. Think about how that looked. And think about how the variable propagation speed is affecting that picture, right? How that signal looks. Okay, so that's an example of kind of some time, equation involving time, giving you this this sort of way of interpreting these things. And we're going to return to these sorts of examples kind of over and over again. The transport equation, as simple as it is actually a really, really nice and instructive example because we can progressively change the speed, right? So the easiest possible thing is having constant speed. Then we can have variable speed like we just saw. Then we can have speed that is proportional to the value of the solution itself, which is going to show us a quasi-linear example. And it's going to show us something that is extremely instructive as for what can kind of arise in a nonlinear case, right? So both of the examples we've seen so far have been linear, so some of the complications that arise haven't really happened. I'm going to do another example of, notice that all of these have been first order equations, and that's what we're going to be doing for a while until we finish this business with the method of characteristics and a few applications. But the thing is that, you know, I have frequently mentioned that it actually doesn't matter that much if we are dealing with first order equation versus like a first order equation with multiple variables, like more than two independent variables. So the order of the differential, the PDE, absolutely matters. Going from order 1 to order 2, that's a huge leap. So like methods are totally different. Like there's all kinds of things that get introduced. So increasing the order of the differential equation definitely leads to crazier, much different type of behavior. But increasing the number of variables in your first order equation doesn't really change anything. In fact, it introduces a little bit more tedium. But other than that, all of these methods that we've used can be adapted for examples having more than two independent variables. In fact, one of your homework, at least one of your homework problems involves this. So it's probably nice that you see an example like this. So here's a quick question. What if I have a first order, and for now we'll say linear, but we can do this regardless of whether it's linear or not. So I'm just going to say first order PDE involving more than two independent variables. That's a bad question mark. The answer here is, well, my process still works. It is just slightly more tedious. Okay. Also, obviously, the pictures become harder and harder to generate. So, um, like we do with most things, we're dealing with a higher order thing. We want to think in higher, say, spatial dimensions. We still just think in 2 dimensions because it's easier to draw the pictures in them, and we just say, okay, like we have a generic n-dimensional region, but I think of it as like some region in, in the plane. When I'm trying to kind of reason through the intuition. Or maybe I think about it as some region in space, right? Space is still not too bad to think about, but okay. So let's see how this works. So the main thing to note is it no longer is nice to use the same notation for variables given. So I'm actually going to intentionally give you an example that uses independent variables x, y, and z, and then we're going to immediately alter them because that's going to make our lives easier. So let's do the following. So let's say we have PD as follows. So find the solution u of x, y, z to the following PD with auxiliary condition. So x u sub x plus 2y u sub y plus u sub z is equal to 3u with auxiliary condition u of xy0 is equal to sine of x plus y. Okay. So how do I do this? Right? How do I do this? Well, the idea here, so first of all, you may say, wait, in the previous examples, we had a region in the plane, and we had to specify data that was typically a function of a single variable along a curve, a data curve. Well, here, this is some u of x, y, z, right, defined on space, and here's my PDE, okay, fine. But then you're specifying data on what kind of object? Well, in this case, you're specifying data on like the copy of the xy plane that sits inside space, right? The z equals 0 plane. So it's a surface, right? You have a data surface, right? Here's, this is a data surface. So I've upped the dimension of, the region that my U is defined on here. So I've upped the region my U is defined on, and then this data surface, right, is now, it's no longer a data curve, it's a data surface. So this region that I'm specifying the data on has also been upped in dimension by 1. Okay. Of course, if I added more and more, more and more variables here, I would have to specify data on like a data hypersurface instead, right? And so you can tell that if I use, say, independent variables, then I specify data on an object that's, say, n-1 dimensional, right? So in this case, 3 spatial dimensions, I specify data on a 3-1 or 2-dimensional object, a surface here, and so on. That's how you can think about this. But in case you're wondering that we're like specifying more than we were in the previous case, no, we're actually specifying like the same amount relatively, right? Okay. So the first step is to replace the notation here because this is not going to be good. There's a z showing up here, but we use z to talk about the characteristic, right, in our characteristic equation. So that's I don't want that. Okay, that's bad. So how do I fix this? I replace x, y, and z with x1, x2, and x3. The usual, right? So this becomes x1 u sub x1 plus 2 x2 u sub x2 plus u sub x3 is equal to 3u. And the auxiliary condition becomes u of x1, x2, 0 is equal to sine of x1 plus x2. All right, so now I've translated it into this notation. This will help me. So then what do I do in my characteristic equation? So now the corresponding thing, right, if we're trying to think about how to do this in a corresponding way, I have characteristic equations here that denote my components, right, of my space, so x and y here. So since I was in the two-dimensional case before, it's natural I would have x and y showing up. But now I need an x, y, z. I need an x1, x2, and x3 showing up, and the corresponding characteristic equations here should work in exactly the same way. So for instance, I have each of these are equal to their corresponding coefficient functions. So then I should have x sub 1 dot is the coefficient function on x sub 1 partial. X sub 2 dot is going to be the coefficient function on the x sub 2 partial, and then x sub 3 dot is going to be the coefficient function on the x sub 3 partial, which I don't have in that form I was just pointing at, but I do have here. So what are the characteristic equations to see how this works? Right. Well, my characteristic equations for x1, x2, and x3, this would be x1 dot is so x1 dot of s is equal to x1. All right. x2 dot of s is equal to 2x2. x3 dot of s is equal to 1. Right? Okay, what is my characteristic, right? It is now parameterized by x1s, x2s, x3s. Okay. Again, so first of all, if I am thinking about solving these, right, I need to specify some initial conditions here. So I want at s equals 0, I want my characteristic to lie where? Before I wanted it to lie on the data curve. Here I want it to lie on the data surface. So I want it to lie on, so here's my function on the data surface. The actual data surface, of course, is the set of x, y, z such that the z component's 0. So this is the x1 versus x2 plane, right? So I want it to lie on the x1, x2 plane. Okay, so i.e. I want like x sub 1 of 0 to be some initial point. We'll say x sub 1 naught. I'll use a superscript. X sub 2 of 0, I want to be some initial point x sub 2 naught. Okay, and x sub 3 of 0, I want to be 0. Okay, so here I have two parameters, right? Instead of just having an x naught that specified my parameter on the data curve, I have a data surface now. So I have two parameters that specify the data surface. Okay, so that's kind of annoying. That just means that when I get to solving these things, I'm just going to have more equations, right, naturally that pop up. Okay, so that's going to be how that works. But let's see what I do here. Okay, so let's talk about solving these. Because these are of a particularly simple form, I can actually solve these no problem, imposing these initial conditions. I'll go ahead and do that. So this tells me that the actual form my characteristic takes, right, x sub 1 of s is going to be x sub 1 naught, right, e to the s, because this is just derivative of function is equal to itself. Here's its initial value. So I know exactly what that is. It's x sub 1 naught e to the s, right? Okay, what about the second one? right? Again, I'm lucky because this system is super simple. Each thing, this is an x of 1 differential equation, only involves x of 1, x of 2 only involves x of 2, and so on. So this is pretty simple to go through and do. Here I have x of 2 dot is equal to 2 x of 2, so this is going to be, so x of 2 of s is going to be x sub 2 naught e to the 2s. And then lastly, of course, this is just going to be, because this is equal to 0, this is x sub 3 of s is just going to be s. Okay. Now, what about the z equation? So for the characteristic equations, there's more than 3. These are just the first 3. The other characteristic equation, of course, is z dot of s is equal to 3z, because my coefficient function on u is 3. So this is z dot of s is equal to 3z, right? And so since I have initial data specified here, my z of s is sine of x1 naught plus x2 naught e to the 3s. This comes directly from here. So, okay, where does this come from? Right, so here, remember, this tells me that z of s is like c sub, I'll call it c sub 3 just because we always did, e to the 3s. Right, that's what this means. But what is this constant? Because at z naught, this has to agree with the data on the specified on the data surface, and on the data surface at these initial points, x1 naught and x2 naught, this would be sine of x1 naught plus x2 naught, right? So that's where this comes from. So now I have to solve, at a generic point, I have to solve for x1 naught, x2 naught, and s. Normally, I just had to solve for x naught and s. Right, so let's do that here. So thus, at a generic point in space, x1, x2, x3, I wish to find an x1 naught, x2 naught, and s corresponding to it. But this is actually easy from this, right? In fact, just from what we have written here, x sub 1 is equal to x1 naught e to the s. X sub 2 is x2 naught e to the 2s. And x sub 3 is equal to s. So I have found s already. And then x1 naught is x1 e to the minus s, which of course is x1 e to the minus x sub 3. X sub 2 naught is x sub 2 e to the minus 2s, sorry, which is x sub 2 e to the minus 2 x sub 3. And x sub 3 is, of course, equal to s. And so, my solution, thus, my solution is u x1, x2, x3 is going to be sine of x1 naught plus x2 naught, which are these two things. So it's going to be sine of x sub 1 e to the minus x sub 3 plus x sub 2 e to the minus 2 x sub 3 times e to the 3s, which is e to the 3x sub 3. Okay, and if you really, really want to, you say, I want to switch it back into original XYZ form, then of course we can do that. So this would be sine of x e to the minus z plus y e to the minus 2z e to the 3z. Okay. So the process works, of course. Had this, had this process been maybe like just a tiny, tiny bit nastier, right, at any of these steps, then it would have been pretty rough to handle. But don't worry too much about that, right? You're trying to learn kind of the overall picture here, so we're not going to focus too hard on some like really, really tedious kind of stuff that could arise if we were being really mean to you, right? So in whatever case you're in, we kind of want to show you the nicest possible thing that can result. Even when we're talking about nastier things, fully nonlinear PDEs and stuff like that, we want to show you like the nicest form of those things so that we can actually say something about them, hopefully, right? So anyway, that's kind of the idea. So you have seen everything now that you would need to attack any of the problems in the first homework. So let me know if you have any questions about any of that stuff. You all were quiet in chat today, which is fine. But like I said, if you have any questions about any of this stuff, either in real time or later, you can email me. Let me know. I posted. So we have a tutor for this class, as I mentioned in a previous announcement. So I posted all that info to the syllabus page, so you can always look at it. So there's Zoom link, all those things if you have any questions about this stuff. But anyway, I think that's a good stopping point for today. So we'll do more stuff with method of characteristics. We're going to be doing method of characteristics for a little bit more before moving on. So the next we'll do semilinear and some quasi-linear stuff coming up, and then maybe dip our toe into like the fully nonlinear case just to see that we can actually still do a lot of this method of characteristics business. We can still get a lot of it done. We have to give it to you in a nice enough form that this actually makes sense. We can actually say something about it, and it doesn't yield some ODEs that are unsolvable or something, right? So that's the idea. Anyway, so that's that. I will see you all tomorrow at the same time. So I'll send out an announcement, hopefully like a couple minutes before 11, and that will be that. So anyway, I will see you all tomorrow.